Yeah, settle in. This will be potentially a long one here. This is a big one. You'll learn today why we teach you to factor, right? Factoring isn't just like to stretch your limbs out, and factoring serves a great purpose in mathematics starting from this point on. And it can be simple like what we're doing, or it can apply itself to even upper degree like cubic and quartic and quintic and sextic and heptic and all those kinds of polynomials. And so anyways, you definitely want to know how to factor. And so having said that, well, today is what, May 3rd? Cinco de Mayo en 2 días. Vamos a comer. Okay? Oh yeah, Star Wars Day tomorrow. How lucky are we? Star Wars Day and then Cinco de Mayo back to back. Anyhow, today is May 3rd.
Yeah.
There are lots of ways to solve quadratic equations. I will tell you the methods that I'm aware of. There is factoring. There is using something called the quadratic formula. There's a process called completing the square. There's also square roots. There is graphing and observing roots on a graph. There's probably more, but those are the methods with which I'm familiar. The one that we're going to talk about this year in Algebra 2, we'll delve way more into quadratic formula and completing the square and making judgment calls and things like that. For this year, I think we're going to call it good if we just stick with factoring. And so the idea today is we're going to solve equations. Before I can get to that, I realized coming in here today, there's one little hole in the education that I've given you so far, and it is polynomials like this. So what I'm putting up here on the board is not solving a quadratic equation. This is going to be a brief, like 2-minute sidebar before we begin the actual lesson, but you want to get this into your notes. If I asked you to factor this, you wouldn't. And that's what you would think. Having sat through my class for the last few days, you would think, and I would say the exact same thing that Kinsley said, and that is, let's do 2 sets of parentheses. And this is a different type of factoring. Do you know what it is?
Yeah, there's 2 and 1 at the same unit, and then 1 plus.
You're going to, how many of you, the show of hands, plan on taking Algebra 2? If you take that class, you'll hear me utter the following 3 letters at least 500 times. And you'll hear me probably say it again at least 100 times this year. And they are, ask anyone who's taken Algebra 2 from me, they are really, really important letters. Because I know that you've heard that before, haven't you? The greatest common factor. Sometimes factoring doesn't involve a whole bunch of 2 sets of parentheses and what multiplies to make this. Factoring can honestly be as easy as just doing the distributive property backwards. Ironically, these are the ones that cause people the most stress. I'll never understand why, because in theory, they should be the easiest. If you look at these 2 terms in my polynomial, what is something that they both have that they could offer? X. So I'm going to take X and I'm going to undistribute it from that polynomial. And if I do that, then I just build a shell and simply rebuild what it would be, yes, had I divided them or pulled out an X. And yes, exactly, Alyssa. The X squared drops to a regular X and the 9X drops to a regular 9. And sometimes factoring can be that easy. Yeah, you're thinking, your mind is stuck right now, which is a good thing, on quadratic trinomials, because that's where we're going to spend most of our time, is on the quadratic trinomials, where you build your 2 shells and you put your X and your 2X, and one's a plus and one's a minus. So that's good. It's just not everything. And so you're going to see some polynomials like this. And these ones we say are missing the constant term, right? You would agree that that's what made that situation unique, is the fact that there is no like plus 18 at the end, or whatever, minus 22 or something like that. That's, bless you, that's more what we're accustomed to. But when you see these come in, the ones that are missing quite specifically the constant term at the end, then that's how you approach it. You simply pull something out. And so let's test our knowledge here. Again, not all factoring means the same thing. If I say factor this, you think, oh, this is one of those weird ones, right? What can I get out of m squared and 3m? I can. And so I'm going to pull out the m. Let me switch colors here to be consistent. I'm going to pull out the m, and then I'm simply going to rebuild the problem. And in case you haven't clicked this yet, it is literally just the distributive property thing backwards. You're undistributing, right? So if I take m squared and pull out an m, he drops to m, and minus 3m is now just minus 3. You follow? Good, good. Okay. So before I begin, let's do a couple quick warm-up factoring problems. I have a bunch here. I told myself I'm not going to do all of these, but let's just make sure you guys are up to speed with how to factor, because if we're not good at factoring, today's lesson and tomorrow and the next week basically is like a throwaway. Factoring is essential. So let's practice real quick. Just as if this were on last night's homework paper, that worksheet that we just graded, let's factor. And this is a regular trinomial. This is our comfort zone, the 2 sets of parentheses, blah, blah, blah. Shouldn't take you longer than about 30 seconds. I'll ask questions like this because it's important to me that you can answer them. What's one really good thing about this problem? Yes, that the 2 in front is a prime number. That's a huge observation because it limits the number of options that we're going to be burdened with having to test. So I know, I don't think, I know that it looks like this. What's something else that I know? Yep, not even up for discussion. The only discussion at the end would be maybe we'll have to switch a boo-hoo, right? And then it's just a matter of like some 3rd grade math. You just got to know numbers that multiply to make 12. 1, 12, 2, 6, 3, 4, and the backwards is of those. Has anyone found it yet? I like this. And if we test the way I have it, I know Alyssa said the right thing and mine's still backwards. But if you test mine, then obviously my signs are off, right? I have positive 3x minus 8x, which makes negative 5x. And so Alyssa had it right. I need to switch my plus and minus to a minus and plus. You just got done doing several days worth of this, so that shouldn't have been anything vexing. Okay, let's try another one. Start to rank these in your mind. You start to develop the ones you see coming and you go, yeah, baby, easy money. Yes. So there's so much redeeming quality about this problem. The first thing is that there's no number in front of p squared. So this is one of these easy peasy ones where I don't have to sweat all that stuff. And then on top of that, they both have to be minuses because they multiply to make positive 36. But of course they add to make negative 13. What are the magic numbers? 4 and 9, of course. There's a lot of numbers that multiply to make 36, but the requirement is that you have to make sure that that times that, which is negative 4p, in addition to that times that, which is negative 9p, of course, adds to make negative 13p. We could sit here and talk about all the other things you wanted to say, like p minus 3 times p minus 12, and we'll continue just to shoot them down, because that makes negative 3p, that makes negative 12p, and those make negative 15p. We could keep going and going and going, only to realize, yeah, it has to be minus 4 and minus 9. Okay. You'll remember these from last night's homework. They were problems 3 and 6 on that worksheet. And I don't have it on the whiteboard over there anymore, but someone had asked about it, and we had decided to make it make more sense to us. We would just put a 0y in the middle. And that helps us to remember what we're trying to accomplish here. If I think of this problem instead as y squared plus no y's minus 121, it becomes pretty clear that I need one positive and one negative because they have to multiply. And on top of that, they have to cancel. What two numbers cancel each other and make 121? 11 and negative 11.
Can't you just square root it when there's no?
Yep, that's what it turns out to be. It's square root plus square root times square root minus square root. Simple, pimple. All right, let's get to it. So that was all just our kind of warm up to get us back in the groove here. Now what we're going to do is solve some quadratic equations. And so we're allowed to use that S word. I hate that people misuse it so often. They say, you put up like 2 plus 2, and someone goes, oh, am I supposed to solve that? And I understand I'm probably uptight about these things, but we sometimes get our math words mixed up. What that person would have meant to say is, oh, do you want me to simplify that? Or do you want me to evaluate that? Those are all acceptable words. We cannot use that S word, solve, until there's an equal sign. And we're trying to figure out what number has to go in place of X to make it work. So for the first time now in your life, you're faced with an equation that has more than one solution. And what you'll discover in mathematics, it's the like fundamental theorem of algebra or something like that, is that whatever the degree of your polynomial is, will determine how many solutions your equation has. So welcome now to the world of equations where you could find one answer. I have infinite faith that just within like 30 seconds, 45 seconds, you all could look at this and figure out, you could figure out an answer, couldn't you? But how? Would you like to take some time and try to mental math it, or should I just show you how to do this? Let's do this. So what we're going to rely upon today and for the rest of our math lives now is something called, some people abbreviate it. I heard my coworker over at Pine, he calls it ZPP. I actually have been teaching for 2.5 decades and I'd never said it until just now out loud. It stands for zero product property. And it is the foundation of upper level mathematics. It's the foundation of how polynomials and functions and their graphs and all this stuff is related. But it is something that a 4th grader could understand. But it's huge. Here's what it says. It says, if two numbers, A and B, multiplied to make 0, comma, then either A has to equal 0 or B has to equal 0. And you could just let that simmer for a minute while you write it down until you fully jump on board with the commonsensical nature of it. There's always going to be the person who tries to find loopholes and exceptions. And I hate to tell you this, but you can't. If I tell you right now in my head, I'm thinking of a multiplication problem. I just now multiplied 2 numbers in my head, and the answer came out to be 0.
One of them has to be 0.
But it's inescapable, isn't it? And it's such low-level logic, but it's foundational to everything that we do. If I have 2 things multiplied together in my head and they come out to equal 0, then one of them has to equal 0. Are we on board? Good. We're going to rely upon this 0 product property for everything now that we do for at least the next week. And in order to make this work, what we have to do is we have to turn this left side of the equal sign into a multiplication problem so that we can rely on the logic of if 2 things multiply to, wait for it, equal 0, then one of them has to equal 0. And this is where that F word comes into play, factoring. Factoring is all about turning addition and subtraction problems into multiplication problems. And this is why we do it. So what we're going to do is we're going to focus on the left side of the equal sign, and we're going to factor. We're going to temporarily put the equals and the 0 out of our mind, and we're going to flex on this problem because we've done like 100 of these. What does the left side factor into? If I just say to you, factor this. Be more specific, please.
So X minus 9.
Yes. And you'll see now the benefits of being good at factoring. If that takes you 5 minutes to find -9 and +4, consider yourself at a disadvantage. So that's what all the practice was for, was to get us to a point where we can say that just as fast as Cooper did. We know there's one positive, we know there's one negative, 4 and 9 make 36. The difference between them is 5. That's it. Now, this is where the zero product property comes into play. If you think about it now, what I've done is I've taken this yellow box, which used to be an addition problem. X squared plus -5x plus -36. The zero product property doesn't apply to addition problems, but it does apply to multiplication. And what I'm now going to tell you is that what's in this green box or what's in this red box, according to the zero product property, one of those boxes has to equal 0.
It has to be either +9 and -4.
Correct. So if I covered up everything on the television, everything, and just said to you, what makes the green box turn into 0? What value could you change X into? The first thing people like to say, not Alyssa this time, she nailed it, but people like to say 0, put in 0. Like, okay, go ahead, get down with your bad self. But if you put in 0 into the green box, what's 0 minus 9? That doesn't work. If I want to make 0, then I change X into 9. Yes. Because it's not a linear equation and there's no way to quote unquote get X by itself. So how we would normally approach a linear equation, which you've done 1,000 of this year, is we would put like all the X's on one side. So it says like 4X and then equals like 32 and we divide by 4, right? But the idea of getting X by itself doesn't apply here. Why? Because there's 2 X's and they're not even like terms to begin with. So how would we consolidate them into one package? Do you understand that? We wouldn't. And I have Algebra 2 students here. Here we are in May at the end of their potentially final year of math in high school who still don't understand that distinction. Linear equations you solve by segregation. You say X's, you go to that side, numbers, you go to that side, and then I'm going to divide by whatever stupid numbers attached to X. You've been doing this since the 8th grade, right? Those are linear equations. This is a quadratic equation and it cannot be solved the way a linear equation can. You have to break it into its multiplicative pieces and then set the pieces equal to 0. And I hope that makes sense. What makes the red box equal 0? -4, right? Not -4, but the number -4. So we have found now the 2 solutions to this quadratic equation. And had I given you an hour and not shown you this trick, could you have figured that out?
No.
I don't, maybe. You probably would have found the 9. Usually people, if there's a positive or negative, people usually find the 9. They go, I got the positive one. I figured that out. But let's check them real quick and just make sure that this is legit so you don't think I'm like yanking your chain. If I take 9 and I put it right, I'll use yellow arrows here, right here and right here. I need your help with some basic math. I'm terrible with my times tables. What's 9 squared? What's 5 times 9? So 81 minus 45 minus 36. What's 81 minus 45? 36 minus 36?
0.
Jackpot. Now the -4 might be a little bit trickier for us to test, right? Let's go find out what happens here. If I take -4 and put it where the yellow arrows are, what's -4 squared? It's positive 16. And then what's this next chunk right here going to say? It's going to say plus 20 because it's minus 5 times -4. 16 plus 20 is 36. 36 minus 36 equals 0. Hot dog. Proof positive that we have 2 different numbers for the first time ever in our lives that make the same equation true. Let's go again. So when I'm looking at my factoring, I know that one of the signs has to be plus, and I know that one of them has to be minus because they multiply to make negative 30. I don't give a hoot about that minus x in the middle. If the back number is negative, then I'm going to roll with that. So that means there's one plus and one minus. What two numbers do I want? Definitely a 5 and a 6, because they'll multiply to make my 30, but the difference between them, the 5 and the minus 6, however you want to say that, is what we want, negative 1. So we have x plus 5, x minus 6. Those are not the solutions. Those are called factors. So what are my solutions? Negative 5.
And positive 6.
Very good. And those numbers, if you plug them back up into the original quadratic equation, we'll both solve it out. Okay. Next one. Factor, 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 factor. I think we should factor. That thing on the left, it's called a difference of two squares, by the way. That's another thing you'll hear me say about 800 times. I'm not worried about you naming it now or anything. That's one of the ones where if you put the 0 m in the middle, then it makes maybe more sense. What does it factor down into? Difference of squares will always predictably factor like this. What then are my solutions? And remember, let's not ever use the words plus or minus when we're talking about the solutions. Plus and minus are verbs. We apply those words to when we're making something bigger or smaller. So m is 9, m is negative 9. No pluses, no minuses. There are positives and negatives. Okay. How about this one? This is what we learned at the beginning of class today. This is this new kind of factoring. You remember what those three magic letters are? GCF. So we're going to pull out a greatest common factor of what? Remember, we're factoring this. What's the GCF? So I'm going to pull out K, and that leaves behind. Good. Now, not to be overly patriotic here with the red, white, and blue, but you see two factors on the board. I'm going to use that word so much until it sinks in. Factor can be a verb. If we're factoring something, factor is also a noun. I'm going to point to something. This is called a factor. You need to know, as a noun, a factor is a physical object that multiplies by something else. And this blue thing is called a factor. And our job is to set the factors equal to 0. What makes the red factor equal 0? It's the stupidest question anyone will ask you all day. What could you put in place of K to make the red factor equal 0?
0.
Yes. So one of our solutions is K equals 0. You might at this point feel inclined to ask the following question. So wait a second, if there's a GCF, if this is one of the GCF ones, is one of my answers always going to be 0? Yes, it is. It's the only way to make a GCF like that equal 0. And what makes the blue factor equal 0? Not minus, negative 4. Good. All right, ready to step it up a notch? That was rhetorical. We're stepping it up a notch. Oops, excuse me, change that to minus, please. Make sure you make a note of that. 5x squared minus 28x plus 32. So something changed, right? Obviously. There's a number in front of x squared now. Dun, 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 dun. That means that the factoring officially gets more difficult. So the fact that there's something in front of x squared means that the factoring just stepped up a notch, but that's okay. We're going to rely on our fundamentals. We're going to say, I have something equals 0. I want to make that something into a multiplication problem. So I will proceed as normal.
minus.
It would have to be a 5x and a 1x, and they both have to be minuses. These are all really powerful pieces of information. A good factor starts by saying he or she says, this is what I know. I'm going in, I know this, I'm gonna write it down. And now it's just a little 4th grade math problem. I gotta find my numbers that make 32. 8 and 4 is a good logical place to start. 2 and 16 is fine too. I heard 8 and 4 first. Where do you want me to put them? Because it matters. Here? Very good. Good. All the practice with factoring will pay off here. And this does work. And thanks to Alyssa, we got it actually very, very quickly. I have 2 factors and I know that they work because, and I'll run through this again for anyone who might be still a little bit gray on this. What do those make when I multiply them? What do those make?
-20.
There's my -20. Nice. So I now have 2 things multiplied together that make 0, which means that I need to make the things themselves equal 0. So let me ask you the really easy one first. What makes him equal 0? Easy. Next one? Weird, right? What makes that equal 0?
Minus 5x plus 8.
Nope. Like you could try, stop saying plus and minus, okay, you guys? The numbers that we're looking for are positives and negatives. They are not pluses, they are not minuses. They are positives and negatives. If I put in +3 like Corbin wants me to, what's 5 times 3? 15 minus 8 doesn't equal 0. I always say to myself, let me write this down and you tell me if I'm crazy. You're not gonna hurt my feelings. Don't I want 5x minus 8 to equal 0?
Yeah.
Is that what I want? Is that what I want? Then write it down. If you want it to equal 0, write it down. 5x minus 8, I demand that you equal 0. This is what algebra is for. You want something to happen, make it happen. Write it down. And then you solve this like a 6th grader. How would you solve that little blue equation? You add 8 on both sides and get 5x equals 8. And then what would you do? You would divide and you get 8/5. So one of my answers is 8/5. And in case you're looking for a shortcut, in case you didn't already discover the shortcut, let me show you something fantastic. I'm about to use my pen and I'm going to do a little vandalizing. Watch out. Imagine that 5 that I just scribbled out was not there. What would the answer be? X equals 8, right? X equals 8. But then you just have to boop, divide by the number that's in front of the X. That's all. Got it? Houston, we have a problem. You say to yourself, well, thanks a lot, wise guy. Like, how am I supposed to use this 0 product property if it's not set equal to 0, right? Of course, you just add 30. So a big part of this is us understanding that we don't proceed until we force the 0 product property into play. And so this is going to involve sometimes a little bit of what we might call some prep work. I say to myself, 5 or n squared, you're good. You're good, minus 11n, but you minus 30. What are you doing over there, you idiot? And so we're going to move it over. And then we're going to factor once we have it set equal to 0. What are the factors? It'd be n and n. They're both minuses. They're 5 and 6. What are the solutions?
Positive 5 and positive 6.
There you go. And you'll coach that out of yourself. Some of you guys, like you hear the weatherman and he says, oh, the temperature outside's minus 10. What should he or she really be saying? The negative 10, right? So try to not follow the bad examples of others. Numbers themselves can be positives and negatives. Pluses and minuses are verbs. They're words that are action words. Okay.
No, you just move the X over.
Yeah, I hope you're still awake and listening because I'm about to tell you something that you really need to hear. It's not about path of least resistance in this case. It's not a really smart person would say, well, let's just move the x squared over because there's only one of him. No, that's not why we move the x squared. Why do you think we'd want to move the x squared? So he goes positive. If you're writing things down and taking good notes today, you never, ever, ever want this term to be negative. That's what we call, remember, the leading term. And the leading term of your quadratic, you need to make it positive. And if that means that everyone has to move everybody. I don't care. So in this case, I say to myself, Mr. Negative x squared, I need you to head over to that east side and become what I want you to be, positive x squared. And then the 2x did not have to move. The minus 35 did not have to move. And if it bothers you that your zero's on the other side, well, I got two things. Number one, A, just get over it, or move your zero. Who cares, right? Doesn't matter. Now it's time for my second favorite F word, factor, right? You don't want to know. So we go into this and we think about only the number in the back. There has to be one positive and there has to be one negative, right, Seth? Isn't that correct? So we're going to put one positive and we're going to put one negative. And my numbers are going to be what? 7. And we want to make sure that the balance is correct. We want to make sure that we give the positive the 7 and the negative to the 5. And then remember, those are not solutions. Those are just called factors. So the solutions are x equals negative 7, x equals positive 5. Got it? How about this one? If you're still listening and you heard what happened in the last problem, then you're aware that this choice is not ours. This isn't a flip of the coin. Someone has to move across the equal sign. Who is it? Yes. And it's sometimes people say, well, I like all my stuff on the left. This is not about the left or the right. This is about saying, I'm going to make x squared or k squared or r squared. I'm going to make it positive. So please let me get caught up to you. Okay, we can't all go fast. So when I move the negative k squared over to the left, I rewrite, and make sure you always write in standard form. The negative k squared becomes positive k squared. The minus 6k did not have to move, and now we're placed and ready to factor. And this is the kind of factoring that we learned at the start of class. What's it called again? GCF. What is the GCF of k squared and 6k? It is. And so I have a factor of k and a factor of k minus 6. So my solutions are
0.
You feeling it?
Yeah.
All right, last one then. Yair, what's the first thing we have to do? Good job. So Yair, if I rewrite this in standard form, set equal to 0, what would it say? The order that we put things in is really important, okay? I put these backwards on purpose, not hoping you'd mess up, but with the expectation that you might, and you get to learn something. You have to put your polynomials as x squared, then x, then constant. So what's next, Yair? You mean plus 37x? Nice. Now that we've crossed that bridge, it's time to factor. You working with us here? They're not equations, they're factors. So there's my pair of factors.
We need 2 pairs.
I need 2 pairs of factors, okay? Like this. So I need what, remember we've been calling these, I think, the templates. So we have 2 templates with which to work here. One of them could be the 6x and 1x template, and one of them could be the 3x and 2x. And we do know that there's going to be alternating signs. Maybe we'll switch them later, who knows? And then the hunt is on, you know? When someone says 35, you probably immediately go to 5 and 7. I mean, 35 and 1 could be what we're looking for. I don't know. Let's try 5 and 7. Did you get it? What factors did you find, Evie? Yeah. So you did the top template, and you have a 5 here and a 7 here. Okay, so you have a minus and then a plus. Okay. Let's check Evie's handiwork before we as a class commit to this, okay? Make sure you had the x plus 5 first. Oh, so you, oh, I'm sorry. So you want my, okay. So you have a 5 here and a 7 here. Is that better now? Thank you. Sorry about that. So let's check Evie's handiwork now that her teacher got it written down correctly, and let's see how she did. Like, again, we're not checking Evie's handiwork to see if she knows that 6x and x make 6x, right? We're not checking if Evie knows that 5 and 7 make 35. Got that. We're checking these, the green things. What do those make, everybody? Yeah, what do these make?
40.
What's -5 plus 42? Nice job. So there's no need for us to check the second template because we've already found the way, well, Evie helped us find the winning combination. And now the question becomes, what solution do I get from the one that I just underlined? 5 over 6. Very good. And then the one that I'm underlining in blue gives us -7. Very good. You guys feeling good? All right. I'm going to stop the recording. I'm going to hand out a worksheet. It is not homework tonight. All right. It'll be something that we work on for 5 minutes, and then we'll work on it some more tomorrow. Sound like a deal?
Yeah.
All right.